In part A, we're asked to sketch a slope field for the given differential equation at the 9 points indicated. So we'll use the values of the 9 points indicated. The x values given are -1, 0, and 1. And then the y values are 2, 1, and 0. And replacing these values into our differential equation, we get the value of 1/2, 1 and 3/2, -1/2, 0, and 1/2, -3/2, -1, and -1/2. So sketching the slope of 0, that'll be a horizontal tangent. Sketching the slope of 1 will be a positive slope. Then sketching a slope of 1/2 will be less steep than 1. Sketching a slope of 3/2 would be steeper than 1. Then sketching a slope of -1, so negative slope, the -1/2 would be less steep than -1. And the sketch of -3/2 would be steeper than the -1. In part B, we need to find the second derivative in terms of x's and y's. So dy dx was 1/2 x plus y minus 1. I'm going to go ahead and derive that. So second derivative of 1/2 x is 1/2, derivative of y is 1 dy dx, and derivative of -1 is 0. Need to be in terms of x's and y's, so we're going to replace dy dx with that expression that has x's and y's. Describe the region in the xy plane in which the solution to all the curves are going to be concave up. So concave up is when the second derivative is going to be positive, so we'll get our second derivative, and we're going to make that greater than 0. Solving for y, so the solutions to the curve will be concave up whenever y is greater than -1/2 x plus 1/2. In part C, we have f of x as our particular solution with that initial condition. The question is, does f have a relative minimum, a relative maximum, or neither at x equals 0? So if we have a relative minimum or maximum, we need to have a critical number. So we're going to take that first derivative and check to see if that point at x equals 0 and y is equal to 1 is a critical number. So replacing in 0 for x and 1 for y, we get the answer of 0. So that point 0, 1 is a critical number. So since we have a critical point, the critical point can go into the second derivative and run the second derivative test. So replacing the critical point into the second derivative, we can determine if this graph will be concave up or concave down, so we'll know if we're going to have a maximum or a minimum. We get the value of 1/2, which is positive, so therefore f does have a relative minimum at x equals 0. So f has a relative minimum at x equals 0 because the first derivative at that point is equal to 0, and the second derivative at the point is positive. So then in part D, we want to find the values of the constants m and b for which y equals mx plus b is going to be a solution to the differential equation. So if y equals mx plus b is the solution to the differential equation, if we derive y, we get m, so this derivative should equal the differential equation. So m is equal to 1/2 x plus y minus 1. Y is just mx plus b, so we can replace y in with mx plus b, then grouping the terms together so that we have the linear terms together and the constants together. So the definition of equality is a constant on the left-hand side would equal the constant on the right-hand side, and the linear term on the left-hand side would equal the linear term on the right-hand side. So then solving for the value of m, and then replacing in that value of m to solve for the value of b.